Okay, so validation and model selection. So we have been discussing two kinds of errors. One is the training error and the other is the test error, right? So the training error is basically the average of your loss on the training examples. And the test error is the expected value of the loss on a fresh sample. And using pack learning in the first part, I should make this full screen. In the first part, we were able to bound the gap between the test error and the training error. So we provided probabilistic guarantees that the test error is small if the training error is small. Now, another approach is to use a technique called validation. So validation is a practical approach to estimate E out of G. So we want to provide a way to sort of practically estimate the test error, right? So what we will do is the following. We are given a training set. So we are given D, which is of the form x1, y1, x2, y2, up to xn, yn. We'll take D, which consists of n samples, and we will divide it into two parts. D train and D val. So the D train will consist of n minus k samples, and D val consists of k samples. So we take our training set, maybe this is 100 samples, we will put maybe 80 in the D train set, which we will use for training, and the remaining 20 will be used in the validation set. So we'll split our original data set into two parts like this. Is this clear? So we have original data set. We'll take some of the samples, k samples, and then usually k is 1/5 of n. 20% is used for validation. And we will store them in a separate file that is never touched during training. The remaining 80% of the samples are used to train a model. Okay? And then once you train the model, you use the output and evaluate the validation error. And you use that as a proxy for the test error. So we have D train. So we will use the training set now, the n minus k samples, and we will apply the learning algorithm. This could be your favorite learning algorithm to output a hypothesis, G minus. Now I have put a minus on top of it, mainly because this G minus may not be the same as the hypothesis we will get if we use all n samples for training. So ideally we have n samples and we should use all of them to train. Each sample can be very expensive, right? This could be like medical records. So if you are actually deploying the model, you should use all n samples. But in order to estimate the test error, we cannot use all n samples. We have to use a subset of them, say n minus k samples only. And then we get an output which won't be the same as G, so I'm calling it G minus. So G is the output if all n samples were used in training, which is ideally what I should always output. You never output G minus, right? This is only used to estimate the test error. So G is not equal to G minus in general. Everyone understands the difference between G minus and G? Okay, so what you do after that is you compute eval of G minus, the validation error for G minus, which is 1 over k summation of xn yn in dval of E of G minus of xn and yn. So what you do is you evaluate the average error you get on the validation set of your output hypothesis trained over detrained, over the n minus k samples that are not part of the validation set. And you call this the validation error of G minus. And what we would like eval of G minus to be close to E out of G minus. So the validation error should be close to the test error. And ultimately this should be close to E out of G. So this is what we care about. We are always going to output the model trained over all n samples. But in order to estimate, we cannot directly estimate the test error for this in this because this is the integral over all data points over an unknown distribution and so on. So what we instead do is we do a two-step approximation. The thing we can compute is the validation error of G minus. So we want to choose k in such a way that the validation error is close to the test error of G minus, because we still cannot compute the actual test error for G minus. We can only evaluate it on the validation set. So we want this to be true, but we also want G minus to be close to G. So we want this, if this is great, but G minus is very far from G, it's not useful, because we will be using, like, ultimately we want to use all samples for training. This is the best model we can produce with all the samples. So this has to be the case. So this is the trade-off we are interested in. Okay, so let's start by looking at some properties of eval and then discuss how the parameters are set. So we'll start like applying various, like the bounds we just saw in pack learning to study the properties of eval. So most of our discussion will be in this approximation. So suppose we are given G minus, this is fixed, okay? Then eval is random since our set dval is random. Right? We are given G minus, which is obtained by training over the training set, and then we compute this quantity and this is a random quantity because the validation set has random points sampled IID. And G minus has no, it depends on D train, which is a completely different data set. So G minus has no dependence on dval. As far as dval is concerned, G minus is some fixed hypothesis coming in. So I'm going to ask you 3 questions We can see, we'll see if you can answer them in any order. One is, let's look at the probability of eval of G minus minus E out of G minus greater than epsilon. This is the first question. Can you bound this? Second is expected value over d eval of G minus. And the third is the variance of eval. So using the results of pack learning and other sort of simple things, can anyone give me any of these results? Can anyone see how any of these quantities can be simplified? So this is, how can you bound this? How can you bound this? And how can you bound this? So the first one, if it is small, it will say that the validation error for G minus is close to the test error for G minus. The second quantity will say that if this is if this quantity is sort of equal to E out, then it means that it's an at least an expectation eval is close to E out. So if this quantity is here close to E out, then it means that in expectation the validation error is close to E out. And if the third quantity is small, it means that the quantity does not fluctuate. If this decreases to the number of samples, then it says our estimate will not fluctuate with respect to the test error. Can anyone think of any, or can anyone simplify any of these? Just have to connect to what you have seen so far. The definition of eval is here. I think you all know what E out is. E out of G minus is the expected value over X of E of G minus of X and Y, where X is just a fresh sample coming from the same distribution. So dval is sample IID, consists of K points. We compute the value. G minus is a hypothesis coming in for eval. Hint is it's a fixed hypothesis because it was trained on D train. It has nothing to do with dval. Yeah.
I guess for the first one would be the soft lines from the earlier, and we can bound it by like 2 times the growth function, the sample, e to the negative.
Yeah, exactly. Just direct application of Hofling with a single hypothesis. So we started by applying Hofling. Remember the the jar example, we were drawing red and green colored balls. Then we connected it to the fixed hypothesis case, right? And we said for a fixed hypothesis, we were directly able to find the connection to that example and apply Hofling's inequality. We then threw it out saying, who cares about fixed hypothesis? This is about learning, and then we went to union bound. The Hofling applied to fixed hypothesis. So this is 2 e to the minus 2k. The only difference is the n gets replaced by k because the size of your validation set is k instead of n. Okay. E out is basically the test error, right? So the expected value of eval will be E out. So you have G minus is a fixed hypothesis and you're evaluating it on k random points. If you take the expectation of with respect to any of those k terms, it's all E out. right? This is like the first example we did. We had a fixed hypothesis coming in. We had k random points. This is like our training error on those k random points. And this is the test error. And what we said is the difference between the training error and the test error deviating from epsilon is bounded by Hofding. That's all it is. So E out is this quantity. It's the test error. People see this? Very good. So let me write it down on the next page. So for part 1, G minus is fixed hypothesis with respect to dval, which is like k samples that are IID from the same distribution as the training data. Eval of G minus is like the training error of G minus on k IID points. Okay? E out of G minus is basically the test error on a fresh sample. And hence, Hofding for fixed hypothesis directly applies. You get probability eval of G minus minus E out of G minus greater than epsilon is 2 e to the minus 2k epsilon squared. It's exactly the same identical setting. So anything that is not clear, you can ask now. This is a good exercise to make sure you understood everything. In fact, more of this will come. What about the other two terms? So the second term, let's look at the second term. I'll give you time to think. What do you think is expected value of eval of G minus going to be? E out of G minus. Right? So what this is saying in expectation, this is a random quantity because G minus is fixed, but dval is random. And getting the expectation over dval. But the expectation is going to equal the test error. And that should be pretty straightforward now because this is a sum over k independent samples and the expectation of each one is E out. So the sum will also have the same expectation. So this is saying again that this is an unbiased estimator, if you will, of E out. That's what's the significance of this quantity. So
just to be sure, that's actually required for the first part.
yeah, technically I should, but this was the thing I expected you to make the most direct connection from what we had been discussing. And this is a little bit hard because you have to think about it. But yeah, that's right. We need this essentially for the first part. So just to complete this derivation, we have expected value of dval of 1 over k summation of xn yn in dval e of G minus of xn and yn. This is what we have. So I can write this as 1 over k summation of x and yn in dval let me do one step at a time. Expected value of dval summation of xn yn in dval e of g minus of xn and yn. Okay. Now this is the expectation over the entire set dval. Once I bring the expectation inside, G minus is a fixed hypothesis. So the only term that is random is x and y. Right? So when I bring the expectation inside, I just have to now take the expectation over xn and yn, or just xn, because yn is function of xn, where I guess n I had to get rid of the screensaver here. And what we will do, just for some simplicity in notation, is that we will assume that, let's say, dval is the first k examples. Does not matter how you partition it, and we'll assume the d train is the remaining examples. Okay. N of them go to dval and the remaining go to d train. Let's just assume the first k go to dval and the remaining n minus k go to d train. So now I can write this as summation of n going from 1 to k. Right? And now this is, for each xn, this is equal to E out. So the overall sum is equal to E out of G minus. Okay, so the third quantity question I asked you is the variance, right, of eval of G minus. This is the variance of 1 over k summation of n going from 1 to k e of G minus of xn and yn. This is what we want to compute. Any idea how this will scale? So this is eval. We take the average over the k examples, first k examples, and then you want to compute the variance of this. So this is what is this quantity? This is the expected value. If you were to write it formally, that's a definition. The random variable minus this expectation, which we showed in the out square. So the idea is, as k becomes large and large, this quantity will converge to this quantity. And we saw that using Hofding as one approach. But if you just want to look at variance, like the fluctuation around the mean, does anybody know how the variance will scale with k? Will it increase with k? Will it decrease with k? Will it be independent of k?
Scales 1 over k.
Basically, this is the sum of k independent random variables, right? x1 to xk are IID. We're evaluating them at G minus, so these are IID. So, and then so you're taking a sum of k random variables. The variance of the sum is the sum of the variances, but then you have 1 over k, which when you take it out, you get 1 over k square, right? So you get 1 over k square times the variance of each one, and so this will basically scale as 1 over k. I won't do the full thing, it's not necessary, it's just to give you an idea of how these terms can be computed. This will be 1 over k times the variance of each of these terms. Okay, so now we have an understanding of what this quantity is. So it is clear that if we want from these properties, if we want eval of G minus to be close to E out of G minus, then K should be large. That is, we should set as many points as we want as we can in the validation set. So the estimate of the validation set will be close to the test error. But there is an issue. We also want E out of G minus to be close to E out of G. As the test error, ultimately G minus is just a proxy for computing the test error. The final hypothesis is always going to be G, which is trained on all the samples. If you are, say, working in, say, a medical application, you may have, like, testing each patient might be very time consuming. So you may have like 100 samples. So just training the model on, say, 80 samples is not ideal. The final output should be on 100 samples, right? So you always train on all the data. So, but we can only estimate the validation error on G minus. So we want this to be true as well. And so for this to be true, G minus should be trained on as many samples as possible. The more samples, if we put like one sample for training and use the remaining invalidation set, this will not train very well, and G minus will be very far from G. So this requires that n minus k is large. Okay, so one method requires that k is large, the other requires that the size of the train is large. And so there is a tension between these two. And in practice, the way we resolve the tension, we set k to be like n over 5. We put 1/5 of the point in validation set and 4/5 of the point in training set. This is a rule of thumb. There is no hard and fast rule, but this is usually a good sort of compromise. Almost always the test error that you will estimate with this approach will be like an underestimate of how well you are doing, because ultimately you are training on all data points and you have a better model. The test error is estimated using G minus, and that will be an underestimate, but that's the best we can do with this method. Any questions? Okay, so next topic is model selection. So we will see how we can apply this idea of validation, estimating the validation error to actually select a model. This is a fundamental question in any machine learning problem. I have some data set with 100 points. Should I use a linear model? Should I use, say, a second order polynomial, a fifth order polynomial, neural network, deep neural network? What should I use? What is the right model to use? It's an inherent question, right? VC dimension sort of provides one way to resolve this answer. So the more complex model you have, the smaller will be your training error, but higher will be a penalty term, and you want to balance the sum of the two. But a more practical approach is model selection. Like in practice, what people often do is they do model selection. And the idea here is, so let me state what it is. So we are given data set D, and we are interested in selecting the best model from some fixed class. So from H1, H2, up to HM, that has sort of the best test error in the end. So we want to do model selection, right? So for example, HI could be polynomials of degree I. And we can go from a linear model to a second order model to an mth order model as one example, right? We have to figure out what is the right model for our data set. And so the idea here, the most common method is to use validation set to select the best model. So again, we take our training set D of consisting of n points, and we partition them into D train. This is n minus k points, and D val, which is k points. And then we use the validation error to select the best hypothesis. So we'll again do the same approach. If we have n points, we might put n over 5 in the validation set and 4n over 5 in the training set. And then our approach is like this. So we take for each m equals 1 to capital M, we do the following. D train is used. It's passed into the learning algorithm. And we get GM minus. So the learning algorithm is for each hypothesis class HM. We apply the learning algorithm on the training D train, which consists of n minus k points, and we get an output hypothesis, GM minus. So for linear models, we will get the best linear fit on D train. For the second order model, we will get the best second order fit. For the third order polynomials, we'll get the best third order fit, and so on. We do it for each hypothesis class separately. We don't take the union of all the hypotheses and find the best one in that class. That's not allowed. We train each hypothesis class separately on the training set and find the output. Okay? That minimizes, say, the training error. Then, step 2 is that we use dval to compute eval of gm minus, which is 1 over k summation of xn yn in dval of e of gm minus of xn comma yn. We do this for each m. Step 3 is now we select HM star as the hypothesis class with lowest validation error. So M star will be arg min of M in eval of GM minus. Okay? So what we are doing now is we have computed the validation error for each hypothesis class in the second step. So for the linear model, we got one estimate of the test error using the validation set. For the second order model, we got another corresponding estimate for the test error. For the third order polynomials, we got its own estimate for the test error. Now for all these test errors, among all these test errors, we pick one with the smallest value. So if we say, think about this, what is happening, maybe I'll write it here. Maybe this is m equals 1, this is m, this is 2, 3, 4, and so on. So m equals 1 is the linear model. These are polynomials of degree f. We get, and this is say eval. Then we get one estimate for the linear models, right? We'll get another estimate for the second order model. We get maybe another estimate for the third order models. But then what happens is if we have too high a degree polynomial, it won't have a small validation error because it will have too much power, it will overfit, and you may end up seeing a higher estimate for here and so on. So in this case, we will pick M to be equal to 3. We will select the hypothesis class with the smallest validation error. Right? Is this clear? So this is what this expression is doing. Arg min eval of gm minus over M in the set 1 to capital M.
What if you have a very, very big M and the value is very low? I mean, what if you have a very large M and the error is very low, and then how can you choose that? For example,
Which error, the test error or the validation error?
validation.
Is continuously decreasing for each M? Or?
I'm not sure. Maybe.
So you will pick mathematically the hypothesis class with the smallest overall validation error. Are you not sure about the definition? I'm not sure what you are asking.
I think maybe as M increase, the validation error they may not change anymore.
Okay. So typically you will select the hypothesis class with the smallest validation error. If two hypothesis classes have the same validation error, you will select the simpler one in your setup. Like if you have a deep neural network with 30 layers and 100 layers and they have the same validation error, you would select the one with 30 layers because the validation error is like a noisy approximation to your test error. So you want to select one with fewer parameters.
But then maybe situations that you overfit.
Yeah, if you have 100 layers, you will overfit. So validation error is a proxy not for the training error, but for the test error. And so typically if the validation error is small, it means you have guarantee that you won't overfit based on sort of the analysis we did here, all this analysis, right? So validation error is a good proxy for the test error. So small validation error means you won't overfit. Okay. So people understand this formula. What we are doing in model selection, we have M hypothesis class, we pick one with the smallest validation error. Okay. Let me draw a figure to explain that. And then there is one more step, which you never forget, the actual compute output hypothesis. Never forget this step. All of this was just done as a proxy to estimate the test error and select the model. What you have to do in the last step is use entire training data D to compute GM star. So now you have selected the hypothesis. You run the training algorithm again. Using the hypothesis class HM star. So in the previous figure, M star was 3. So you now train the third order polynomials on the entire training set of endpoints, and this is what you will output. So never output GM minus. That's not going to be the best thing you can do. Always output the final hypothesis. So just to summarize, another way of looking at the model selection is you have M hypothesis. We first train them using D-train. We get G1 minus here, G2 minus here, G3 minus here, and GM minus here. Then we evaluate them using the validation set, and we get eval of G1 minus, eval of G2 minus, all the way up to eval of GM minus, and then we pick the best HM star. We use the validation errors to pick the best candidate hypothesis. Then we use the entire training set to train, and we get GM star, which is output. This is the idea. This is just summarizing the 4 steps that I had before. You first train each individual hypothesis class separately using dtrain that has n minus k points. You compute candidate output hypothesis. Then you evaluate each of them on the validation set. You pick HM star, and then once you pick HM star, the hypothesis with the smallest validation error, you then use that hypothesis class, train it on the full training set of endpoints, and you get GM star, which is output. Okay. Questions? So we'll take a short break and then continue. Or do you guys want to continue and finish early? How many want to continue and finish early, and how many want to continue and finish early? Okay, 1, 2, 3. I guess half. Then we'll take a break. We'll take a 10-minute break then, and then we'll start at 11:05.